Okay, this video shows how to do the EPR simulation, energy participation ratio, to get the cross-cut, which is the frequency pulled by the qubit on the resonator or vice versa. So we already have a chip generator in the Qiskit metal, right? So now we will just want to look at the EPR of this qubit with its resonator, and this resonator is coupled to the fifth rule 9, right? So in order to do the simulation, make it faster, also less messy, before we already showed that we try to run the eigen mode, and we showed that they're well separated. This circuit works well. So we are not going to simulate all the qubit together and all the resonator together. So we will only simulate this part. Okay. So the first thing that I will do is import the EPR program. Module, right? And then we define the design. You can also use this Q geometry table to see what are the junction that you have already made in Qiskit metal, right? By default, they all have 10 nanohenry. Now, then we have this command to assign the name. This is just the name for the inductance and capacitance of the Josephson junction. Okay, so this is still in the Qiskit metal. Taking time. Okay. And then now we are setting up the simulation for the HFSS. So here we can change what we want. For example, we change it to the maximum pass to 15, delta frequency to 0.05. Here we can further change the value of each of these variable. Okay, so this is just as an example, right? Now I can also actually here I actually have duplicator, but anyway, I can put it in the same section for the setup. But here is like, okay, I want to run for 3 modes. For example, now I assume that I have a qubit mode, I have a resonator mode. I just run for one more mode to just make it clear to see that the simulation result makes sense, right? So that is what I'm going to do. I just say NU3. And then after that, what we are doing here is that we will run the eigenmode simulation, and the project is called Qubit, and we just send the component that we want. I just told you that we only want to simulate this part, right? So I don't want to send everything to the HFSS. So now it is running. So let's wait a little bit when it bring up the program. Okay, so it is up, and now it will first do the rendering. I will do fit all. Maybe too early. Now it's going to render everything. In principle, you don't need to add this hanger, but this coupler, but I was too lazy to take them off because the way we wrote it was like coming together. So they are just still there for other resonator, which should not affect the simulation result. So it's doing the resonator rendering, the launch pad for the fifth rule 9, the transmon qubit, and then eventually the silicon and the vacuum, right? So we can take a look what we get, right? This is pretty automatic. If you look at the boundary condition, right? This guy is for the as the Josephson junction, right? So if we double click it, then it tells us that it's using these 2 parameter, Q1 bottom LJ and Q1 bottom CJ. So what are they? So we go to HFSS. Actually, it's in the bottom also, right? Or you go to HFSS, design properties. Q1, sorry, what's that? Q1 bottom LJ is 12.5, and Q1 bottom CG is 8 picofarad, right? This is what we use in our design. We assume the CJ is 8 picofarad, and then after all the calculation, the LJ is about, should be 11.6, not 12.5. So I put in the wrong thing. No, actually it's right, because it should be Q. I put it at the wrong place. It should be Q1. This is Q1, right? So let me just abort it. I don't want to do let me see. Let me abort it, right? We don't run it yet. So I'm going to put this to be HFSS design property Q1 bottom, right? This one should be 11 point, double click it, 11 point, what is that? 6 or 5? 11.6 Henry, narrow Henry, right? So we do this and then say okay. Now it becomes 11.6, right? So now we will try to run it again. I say analyze all, and it forced me to save somewhere. Okay, fine. Then I just save it here for now. But in this case, I might lose the communication with the notebook, right, because of the error. So let me, which is okay. I think because I should be able to run again from here later, right? So let me stop it again, just abort it, right? So I have done some modification. Originally, in principle, I want to show that I can do more modification, and then I can continue to run the simulation again, right? So now I'm aborting it, and I want to see if I can do that, because there was an error. I hope the communication is still there. So let's hold a little bit until the abortion finish. Let me just pause it. Anyway, let me see if I can run the second one. Okay, so try to run it. Okay, it just run from scratch, so let's just use this one, right? Here it just takes time to abort. Okay, anyway, when it is running, right, we can start looking at some of the results. For example, let's look at the eigen frequency. So I'm going to plot adaptive path, plot it as a function of path. We have 3 modes, right? Remember? So we click 3 modes and then say new report. Now it is running. Definitely the third mode has to be a very high frequency one, right? And then the lower mode, lower 2 modes, one will be the qubit and one will be the resonator. Okay, and let's just wait a little bit to see how much it will go. We're using 15 passes, so it's going to take some time. So I'm going to pause it, not to waste your time watching this video. Okay, great. It converged already, and it stopped at 14 because it reached the convergence criteria. Okay, so now we will just do a measurement marker, add marker. Look at this. This is 6.8 gigahertz, 6.87. This is 4.27, right? So it is pretty good, pretty close to what we want, because our goal is 4.5 gigahertz and 7 gigahertz for the resonator. Qubit is 4.5. So it's not bad, right? The design. Maybe some simulation error, or the design is not perfect. It's also, again, instructive to take a look at the distribution of the electric field. Although we did that in another movie, another video, right? So I got highlight it, and then I want to unselect this vacuum, and then right click, and then say plot field, right? Plot magnetic field. We just need to plot one of them, and it's just running. Let's take a look. So here, let me use log scale. Right. So you see that this must be the qubit mode, right? Let's see if that's the case. Go to HFSS, result, no, field, and then add this source. Yeah, we put 1 joule to the mode 1. So this is the qubit mode, right? Then how about for the resonator mode? Is the second one the resonator mode? We believe it is, right? But it's good to plot it. Apply. Great. You see the energy in the resonator, right? How about the third mode, which I also don't know what it is, but it can be one of those coupler, right? The hanging coupler that are not connected to anywhere. It can be something like this, but let's take a look. I don't know what it is, some hybridized mode or something, right? But this is not something we are interested in. As long as the frequency is high enough, right? If you look at this, it's like 12 gigahertz, so we can ignore it. Good, right? So this looks like just an eigenmode simulation, but with this we can do the the EPR analysis, right? We just modify it manually, so you can do many things, including to add the lump RLC, which we have not done it yet. But let's do it so we can see the Q estimated, the Q of the qubit, right? Because we want to know the quality factor of the qubit, so this is important. So here, let me just what do I do? Right click, plot visibility, remove it. Now, in order to do the Q, I need to have couple it to the outside system, and what we will do is to add RLC port, right? So I zoom into here. This is the input of the 349. Then I will try to add a square, right? I do want to add something, not just long model. So I click here. Okay, escape one more time. Zoom in more. Click here. Okay, somehow, okay. Right, and then I move to here and then zoom in. Okay, on this. I say right click. I will say I think I assign it. I don't want to do it as long model. If I try to say lump RLC, they won't let me do it. So I need to delete it, right? Because long model doesn't work. So let me just delete it. Let's do it one more time. And HFSS does not allow you to convert long model to something else, okay? So I don't want to have long model. I can just start with vacuum, doesn't matter. Okay, on this, do you want to create a long model? I say, do you want to create? I say no, right? I do want to create something that can be used. Then I pan to here, escape, and then zoom in, pan a little bit. My mouse doesn't work. Okay, right click, and then I say assign excitation. No, assign boundary, and then lump RLC, right? So I say this is a 50 ohm system. I mean input, and then zoom out, pan, and then I want to draw a line, escape, so I can draw it all the way to here. Zoom in, click on this, a little bit off, but okay. That's one of the pots, and then I fit all because I want to add to another pot. So I'm going to add this rectangle starting from here. Some more, zoom out, pan, and then escape, zoom into this region, and I don't know where I am now. Okay, So keep this like this. Okay. So right click and then assign boundary, lump RLC, 50 ohm, new line, and then I'm going to move it to here. Then escape, click here, and then I don't know which one is a straight line because now this is not a 2D plane. Okay, then just okay, but it doesn't matter. Okay, good. So now I have this lump RLC port, right? As you can see, two of them, right? So I will do this. I can run it again, right? But instead of just to save time, so this time I'm not going to run for such a good convergence, right? I will just run for 1% and maybe let's just stop at 9 because with or 8 because with this one it is going to with the Q it's going to take longer to run, right? Just as a demo, then I think it's okay, just run it in this way. So I just say analyze all and then you will run again, right? In principle you can go back to the notebook, right, and then submit it again actually, right? But that's fine. I will just run it from here. It's the same. And again, I will pause it while it is running to save you time from watching the video. Okay, it has finished because we did 1% error. Let's take a look how many passes it took. Only 8 passes, right? It said it does not converge because we need a few more passes. But because of time, let's just do this. But again, right? Let's look at the mode. The lower one is, yeah, indeed, it has not converged, right? The lower one is, is a little bit too low, 4.1, 6.3. It doesn't matter if you want to spend more time, you can just go to setup and then change the maximum number of passes to 12, right? And then run it again. You won't start from beginning, you will start from pass 9. Okay, this is good. Now, but what I want to do now is to plot the quality factor, right? So again, now we have eigenQ, right? Select all of them and then do the adaptive parsing, new report. Okay, I need to change this to pass and then apply traces and then update. Right. Of course, it has a large range that double click, left button double click and then change it to log. Right, that will be easier to see. Now, Q1, what is Q1? Q1 is big deal, right? It's the qubit. Okay. Now it is very large. That's good because we want to have a very high Q. We don't want it to lose the information, right? So marker, add marker. So Q1 is about what? 20 million, 2E7, 1.8E7, right? So this is good, right? So that is the Q that we have. And then Q2, which is this one, I need to click here. It's lower about 20,000, but that is what we got earlier in our another video, right? When we designed the resonator to fit 9. This is not converged yet. It's still dropping a little bit, right? So we better let it converge, but it's good, right? That is the purpose of this tutorial. And now we go back to the notebooks. Then we can run EPR, right? So in EPR, we will just specify what are the variable, right? On it. Actually, to be frank, I don't know if I need to do it again, but you better just do it because it works. So I run it, set up the junction. I need to delete the JJ. Somehow it has something called JJ. I need to delete it. So this 38 actually no need to be there. I delete JJ and then I add back JJ with what I had here. Okay, so I run it again, and then we run the EPR. Now it's running the EPR. It will do something from here because it try to get the data from here, right? But it's pretty quick because we are only using 8 cosine and the fault space is only 7, right? But anyway, so let's look at the result. We have 3 eigenmode, right, as you can see here. and then you try to calculate the energy participation ratio. I did not get warning saying that it does not converge or whatever. So I just keep going down, right? I come to here. Now, what do we get? We also can ignore this. Now, then it has two. One is using numerical method, another use the analytical method. Now, what we want to see is these two elements, right? Because the first one is the qubit, and then second mode, third mode. So this is the qubit mode coupled to the resonator. Is 1.2 megahertz. Numerical method give me about 1.0 megahertz. Not too bad, right? Although qubit frequency and the resonator frequency are off just because I did not have enough passes, right? So after this tutorial, I'm going to run more. And I'm pretty sure that it will be close to 7 gigahertz and 4.5, right? We were targeting 4.5 after that, right? But that is how I get a crosscut. Okay? Now, if we now, I still have this Q issue. I need to fix this, but that's okay, right? We don't need that for now. I think some problem with my code, but we get a crosscut already. Now, if you go back to this spreadsheet, we also had some equation to calculate the crosscut chi, right? So what we got from that equation is about 0.8 megahertz. HFSS simulation gave us how much? 1 megahertz, right? So it's pretty close. So I'm pretty confident about that. I mean, kind of, okay? Okay, so that is the tutorial for the EPR.